energy. Say it out loud, and it sounds solved. It sounds like something you could hold, weigh, bottle. It is the word stamped on every equation in every science you will ever study. The word behind the light in this room, the warmth in your chest, and no physicist alive can tell you what it actually is, not what it does. What it does, they can tell you in exhaustive, exact, decimal perfect detail. What it is, the substance of it, the stuff of it, remains, after more than 3 centuries of trying, completely unknown. That is not a gap in the textbooks. Richard Feynman, one of the most decorated physicists of the 20th century, a man who helped build the machinery of modern physics with his own hands, wrote this in his famous lectures that in physics today, he was not being humble. He was being precise. And what should unsettle you is that nothing has changed since he wrote it. The equations got better. The measurements got more exact. The mystery did not move an inch. Here is where this goes. We will walk through the fields that may be the true fabric underneath reality, and how you, right now, are a pattern of vibrations. We will discover that so-called empty space is never empty, that it seethes and pushes back against a piece of metal. We will meet the worst prediction in the history of science, a number so wrong it is almost embarrassing to say out loud. We will sit with dark energy, the unseen hands stretching the universe apart, unidentified, unexplained, and yet accounted for in nearly 70% of everything that exists. And we will end at the edge of it all, at a law everyone trusts, that may not be quite as absolute as you were taught. If wonder like this keeps you up at night, take a moment to like and subscribe. We begin. Start with the atoms in your hand. Right now, as you sit with this, the molecules in your fingertips are jittering. Your blood is carrying oxygen through a furnace of chemical reactions. Your brain is spending roughly 20 watts just to follow these words. All of that costs energy. All of that is energy. In some sense, physicists agree to use loosely, carefully, and, if they are honest, a little uneasily. We talk about energy as though it were a fluid. We say things like, the energy flowed into the room, or she has a lot of energy today, and the language itself smuggles in an assumption that somewhere there is a thing called energy, a stuff, a substance, sloshing from one place to another. It isn't a fluid. It isn't a particle you could isolate on a slide and place under a microscope. It isn't a fuel sitting in some cosmic tank waiting to be spent. When physicists write down the equations that describe it, energy behaves like a property, a number attached to a system, calculated from how fast something moves, how high it sits, how tightly its particles are bound together. You can compute it. You can add it up before an event and after an event and find to a staggering number of decimal places that the total never changes. Not the way you can point to a rock or a photon or an electron. There is no energy particle. There is no field you could scoop up in a jar labeled energy. If you asked a physicist to hand you a sample of pure energy, not light, not heat, not motion, but energy itself, stripped of any of its costumes, they could not do it because there is no naked version. Energy only ever shows up wearing something else. This is why Feynman's confession lands the way it does. He was not saying physics is incomplete in some minor, fixable way, the way you might be missing a decimal in a difficult calculation. He was pointing at something stranger, that the single most important quantity in all of science, the number every conservation law is built around, the number that determines whether a chemical reaction happens or a star ignites or a rocket clears orbit. He went further than that single line, in fact, and a fuller passage is worth sitting with. Energy, he wrote, is an abstract thing, expressible only as a number, and it does not tell us the mechanism or the reason for the various formulas we use to calculate it. He compared it, famously, to a bookkeeping problem. A child with a fixed number of toy blocks, who loses some out the window. There is, he said, no block you could point to called energy. There is only the accounting. Physicists have not walked that comparison back in the roughly 7 decades since Feynman first delivered it to undergraduates. If anything, quantum field theory, developed and refined in the decades since, has made the accounting far more sophisticated and no more concrete. You will not find anywhere in the physics literature a rebuttal that says, actually, we now know what the stuff of energy is. The number has only grown more powerful. Because if energy isn't a substance, the next question is unavoidable. What then is doing the actual physics? What is out there, filling space? Physicists have an answer to that one. It is one of the strangest ideas in all of modern science, and almost nobody outside a physics department has ever really. Forget for a moment the picture of the universe as empty space with objects scattered through it like furniture in a room. That picture is intuitive, comfortable, and, according to the physics that has been tested to extraordinary precision for a century, the modern picture says this space itself is filled everywhere with invisible fields, an electromagnetic field, an electron field. These fields are not made of anything smaller. They are, as far as anyone has ever measured, fundamental, the floor of reality with nothing underneath. A particle in this picture is not a little ball of stuff traveling through empty space. A particle is a ripple. Pluck the electron field just right, and you get an electron pluck, the photon field, and light appears. There is no pond beneath. The pond, there is no smaller thing the field is made of. The field simply is everywhere, always, and particles are what happens when it moves. And energy, here is the piece that should genuinely unsettle you. Energy is, in this picture, essentially a measure of how hard those fields are vibrating. A calm field, barely stirring, corresponds to empty, feeling space. A field vibrating violently corresponds to particles, heat, light, motion. All the things we usually think of as energy. Which means you, reading this, your body, your thoughts, the neurons firing as you follow this sentence are not really separate from the fields around you. A knot of vibration in fields that fill every cubic inch of the room you are sitting in, threading through your skin, your bones. This is confirmed physics. Quantum field theory is one of the most rigorously tested frameworks humanity has ever built, verified to better than one part. And yet, almost no one who is not a physicist has ever been told plainly that they are made of vibrations. Here is the part that matters. If particles are ripples in fields, and energy is the intensity of the ripple, then energy was never a substance to begin with. It was always a description of motion in something we cannot see, cannot touch. The mystery hasn't been solved. It has been pushed one layer deeper into the fields themselves, which physicists can describe with beautiful mathematics. Consider what this means for something as ordinary as the light reaching your eyes from a lamp across the room. That light is a ripple in the electromagnetic field, and the field itself, according to the equations, was already there before the lamp was switched on, filling the space between you. Switching on the lamp did not create a field. It disturbed one that was already invisibly everywhere. The same is said to be true of every field physicists have catalogued: the electron field, the quark fields, the fields for each of the forces. Reality on this reading is not mostly empty with occasional objects in it. It is entirely full at every point, with fields that are usually quiet enough that we call the result empty space, and every object you have ever touched is simply a place where one or more of those fields is for a while ringing loudly. Physicists sometimes call this the field-first view of nature, and it is not a fringe interpretation. It is the working assumption behind the standard model of particle physics, the framework that has correctly predicted the outcome of experiment. Ask a working physicist what an electron really is beneath the equations, and the honest answer many will give you is, now go smaller, past the field, past the ripple, into the particles the ripples correspond to, into a single proton, one of the two building blocks along with the neutron. You were probably taught at some point that a proton's mass comes from its ingredients, 3 quarks bound together, their individual masses adding up to the proton's total weight. It is also, physicists have confirmed, through decades of experiments at particle accelerators, almost entirely wrong. Add up the masses of the 3 quarks inside a proton, the numbers physicists have measured with extraordinary care, and you get roughly 1% of the proton's actual mass. The other 99% is not stuff at all. It is energy. Specifically, it is the energy locked inside the force binding those quarks together, carried by particles called gluons, confined so tightly and moving so violently. This is where Einstein's most famous equation stops being a slogan on a t-shirt and becomes something almost vertiginous. E equals mc squared is usually read one direction. Mass can become energy, the way a nuclear reactor or a star converts a sliver of matter into a flood of light and heat. But read it the other way. Energy can become mass. And inside every proton in your body, that is exactly what is happening. Continuously, right now, holding you together. Which means, when you weigh yourself, when you feel the solid heft of your own body, when you press your hand against a table and feel resistance, you are, for the overwhelming majority, not matter in the old-fashioned sense of little solid balls bumping into each other, bound, confined, furiously active energy. Physicists confirmed this through what is called lattice quantum chromodynamics, enormously demanding calculations run on some of the most powerful supercomputers on Earth that model the strong nuclear force inside a proton from first principle. The results match experiment to a striking degree of precision. This is not a fringe idea. It is the standard understanding taught in graduate physics programs around the world. And yet, walk up to almost anyone on a street and tell them that 99% of their mass is not stuff, but the energy of a force they've never heard of, confined inside particles, too small to ever see directly, and it will sound like science fiction. It is not science fiction. It is the confirmed working physics underneath the solidity of your own bones. Push on the number itself. Take an ordinary adult body, roughly 70 kilograms. 99% of that, nearly all of it, is, by this accounting, confined gluon field energy. Only about 1 kilogram, spread across your entire body, comes from what you might call actual matter, in the sense of the fundamental mass carried by quarks and electrons themselves. You could remove that 1 kilogram's worth of intrinsic mass, if such a thing were possible, and you would still weigh nearly what you weigh. It was about how furiously the force holding your quarks together happens to be seething, confined into spaces smaller than a trillionth of a millimeter across. This is confirmed by particle accelerator experiments going back decades. Facilities that smash protons together at velocities approaching the speed of light and reconstruct from the wreckage. The gluon field's contribution is not a rounding error or a minor correction. It is nearly the entire story of what a proton weighs. Because if that much of what you are is really energy in disguise, the next question circles back to the beginning, sharper than before. The answer, it turns out, is even harder to accept. It is hiding inside nothing at all. Picture the emptiest place you can imagine. Not a vacant room, not the upper atmosphere, but true vacuum. The near total emptiness of deep space between galaxies, scrubbed of every atom. Quantum physics says that space is still not empty, not even close. According to quantum field theory, the same framework that describes the fields making up you and everything around you, even a perfect vacuum, has what is called zero-point energy. They tremble faintly everywhere, forever, even with every particle removed. And out of that trembling virtual particles are said to flicker into existence in pairs and vanish again almost instantly. This sounds like the kind of thing that stays safely inside a chalkboard equation, untestable, a mathematical convenience with no bearing on the real world. The effect is named after the Dutch physicist Hendrik Casimir, who predicted in 1948 that two uncharged metal plates placed extremely close together in a vacuum should be pushed toward each other by the very structure of empty space. The reasoning is subtle. The plates restrict which vibrations of the underlying fields can exist in the gap between them, while the vacuum outside is unrestricted, and the imbalance produces a real, measurable force, not friction, not gravity, a force generated by nothingness itself, pressing. For decades, this stayed a theoretical curiosity, until 1997, when the physicist Steve Lamoureux measured the Casimir force in the laboratory. The vacuum push, emptiness, in a very real sense, has a texture. It has a temperature, in some readings of quantum theory, and something that behaves like a pressure, exerting a small but genuine mechanical force on ordinary matter separated by nothing at all. Sit with that. The emptiest possible container the universe can offer is not still. It is not silent. It is a churn of energy so persistent that physicists confirm its existence by placing two plates a fraction of a hair's width apart. There is a further, stranger implication buried in the Casimir setup that rarely makes it into casual conversation. The force only appears because the plates are close enough together to restrict which vibrations of the field can exist in the gap. Longer wavelengths simply do not fit between them, the way a wave too wide for a narrow canyon cannot pass through. Outside the plates, in the open vacuum, every wavelength is allowed, and so the trembling of the field is in a certain sense richer there than in the gap. The imbalance between a restricted inside and an unrestricted outside is what produces the push, which means the strength of the vacuum's activity is not fixed and absolute. It depends in part on the geometry of whatever boundary you place inside it. Empty space, in other words, responds to its container. That is not a property most of us were ever taught nothingness could have. Modern experiments have pushed this even further, measuring not just the static Casimir force between still plates, but what is called the dynamical Casimir effect, real photons pulled directly out of the vacuum, confirmed in a Swedish laboratory in 2011 using a superconducting circuit oscillating at a significant fraction of the speed of light. Actual particles of light created from nothing simply by moving a mirror-like boundary through the seething vacuum fast enough, the result matched theoretical prediction closely. Here is the part that matters. If empty space carries energy, real, measurable, force-exerting energy, then it has an actual numerical answer, one that physicists can calculate directly from the equations of quantum field theory. And when they did the calculation comparing what the vacuum should weigh against what astronomers actually observe warping the cosmos, they got a number so wrong that most physicists who work in this area still call it, without exaggeration, here is the number, stated plainly, because it deserves to be heard exactly as it is. Quantum field theory predicts that the vacuum of space should carry an enormous amount of energy, the accumulated hum of every field's zero-point vibration, added up across every possible wavelength. When physicists calculate this and compare it to what cosmologists actually measure the universe's vacuum energy to be the small specific value needed to explain how galaxies drift apart at the rate we observe, 20 followed by 120 zeros, a number so large it dwarfs the count of atoms in the observable universe, dwarfs it by trillions upon trillions. This is called the cosmological constant problem, and physicists, including Steven Weinberg, who examined the puzzle in a landmark 1989 pascals per second till cited today. To be clear about what this means, this is the theoretical machinery that correctly predicts the magnetic properties of the electron to 11 decimal places. Something is cancelling almost all of that predicted vacuum energy out. Something is suppressing 10 to the 120th power down to something small enough that stars can form, atoms can hold together, physicists do not know what that something is. There are candidate ideas, symmetries not yet discovered, cancellations from physics beyond the current standard model, anthropic arguments suggesting only universes with a small enough vacuum energy. None of them closes the gap on solid experimental ground. This has stood unresolved since physicists first understood its scale in the late 20th century. Entire subfields of theoretical physics circle around it. And it remains, as of today, the single most embarrassing, most unresolved number in the discipline, a number so large that if you tried to write it out as zeros at 1 per second, to grasp just how strange this discrepancy is, it helps to compare it to the most successful calculation in the history of physics. Time agreement so precise that Feynman himself once compared it to measuring the distance from New York to Los Angeles. The vacuum energy calculation uses closely related mathematics built from the same quantum field theory. And it is wrong not by a hair's width, not by a mile, not by the distance across the country, but by a factor that has no comparably intuitive analogy, an error so large that physicists, when they first fully reckoned with it in the 1980 seconds and 1980 seconds, largely assumed there had to be a simple missing piece, some overlooked symmetry that would cancel the huge numbers down to size. Decades of searching have not produced that missing piece. Some suspect it involves physics beyond the standard model entirely. New particles, new symmetries, structures we have not yet detected. Others entertain the more unsettling possibility that no such tidy cancellation exists at all, and that the small value we observe is simply one outcome among many in ways current physics. Because whatever tiny leftover, correctly sized vacuum energy actually exists, the sliver that survived that catastrophic near-total cancellation appears to be doing something. And when astronomers went looking for what was pushing the universe apart faster than gravity alone could explain, they found something. In the late 1990 seconds, two independent teams of astronomers were doing something that sounded almost administrative, cataloging distant exploding stars called Type 1 supernovae, using their reliable brightness to measure distances across the cosmos, mapping out exactly how the expansion of the universe had slowed over billions of years. Except it hadn't slowed, it had sped up. The observation, confirmed independently by both research teams and later recognized with the 2011 Nobel Prize in Physics, showed that the expansion of the universe is accelerating. Galaxies are not just moving apart, they are moving apart faster and faster. In defiance of the simple expectation that gravity should be gradually pulling everything back together, or at least slowing the drift, physicists named it dark energy and named it largely before they understood it, a placeholder label for an effect they could measure precisely. Multiple independent lines of evidence, supernova surveys, detailed maps of the cosmic microwave background left over from the early universe, Roughly 68% of everything in the universe by energy content is dark energy, not stars, not planets. Dark energy alone accounts for more than 2/3 of the total energy budget of the entire cosmos. Named, measured, confirmed by multiple independent methods that agree with each other to a striking degree, and utterly unidentified. The leading candidate ties it back to that vacuum energy we just discussed, the tiny surviving remainder after the catastrophic near cancellation in the cosmological constant problem. Under that reading, dark energy is simply the energy of empty space itself, pushing space apart, because that is what a positive vacuum energy does, according to Einstein's equations of general relativity. Other physicists propose that dark energy is not a static property of the vacuum, but a dynamic field, sometimes called quintessence, that could change in strength over cosmic time. One reading says it is fixed and eternal, tested by ongoing large-scale surveys designed specifically to catch it changing. If it does, here is the part that matters. The majority of everything that exists is made of something we cannot see, cannot directly detect, except through its gravitational fingerprint on the largest structures in the universe, and cannot explain at a fundamental level. We gave it a name so we could talk about it. We have not yet earned the right to say we understand it. It helps to put the full energy budget of the universe side by side, because the proportions themselves are almost absurd once you say them plainly. Roughly 27% dark matter, itself an entirely separate mystery, detected only through its gravitational pull on galaxies. That leaves ordinary matter, every star, every planet, every living thing. Every living thing, every living thing, every living thing, every living thing, every living. The stuff we can see, touch, weigh, and build telescopes out of is the minority footnote in the universe's actual ledger. 95% of everything is something we still cannot fully explain, sitting quietly behind the visible world, doing the work of shaping it. Because if the universe itself is expanding, stretching space between galaxies, then something else happens to energy that most people have never been told, something that quietly breaks one of the most sacred rules in all of physics. Everyone learns at some point that energy is conserved. It cannot be created, it cannot be destroyed, it can only change form. Chemical energy into heat motion, into sound, sunlight, into the sugar inside a leaf. This is one of the oldest, most trusted, most thoroughly tested laws in all of science, confirmed in laboratory after laboratory, in every corner. The mathematical reason it holds is not arbitrary. It comes from a discovery made in 1918 by the German mathematician Emmy Noether, a result now known as Noether's theorem. Noether proved that every conservation law in nature is tied to an underlying symmetry, conservation of momentum. And conservation of energy comes from the fact that the laws of physics look the same no matter when in time you are standing. If the rules of physics do not change from one moment to the next, then energy Noether showed must be conserved. Here is the asterisk almost no one is told about. In an expanding universe, our universe, that time symmetry does not perfectly hold. Space itself is stretching, growing, changing, and when that symmetry breaks, so does the guarantee. The clearest example, light traveling across the universe from a distant galaxy, is stretched by the expansion of space itself. As the light stretches, its wavelength grows longer and its energy, tied directly to wavelength, genuinely decreases. This is measured, confirmed, uncontroversial among physicists who study cosmology. The light arrives at our telescopes carrying measurably less energy than it started with. The question that makes physicists uncomfortable in an ordinary, non-expanding system, lost energy always shows up somewhere else, converted into heat, into motion. In an expanding universe, physicists, including Sean Carroll, who has written extensively and plainly on this exact puzzle, argue that the energy carried by that stretched light, it does not go anywhere. It is not transformed into another form waiting to be tallied. In the framework of general relativity, total energy of the universe may not even be a well-defined quantity to begin with. There may be no global ledger to balance in the first place. To be fair to the other side of this, some physicists resist that framing, arguing that with the right, more careful bookkeeping, the debate is genuinely unresolved. Argued in physics journals to this day, one reading says the law truly breaks on cosmic scales. Another says it is preserved once you account for gravity correctly. What both sides agree on is this: the tidy version of energy conservation taught in every introductory course. It is worth naming just how counterintuitive this is, set against everything else you have ever been taught about energy. Every laboratory experiment, every engineering calculation, every rocket launch and power plant and battery on Earth relies on energy conservation, holding exactly, without exception, in local bounded systems. Noether's proof is not being overturned. What is happening instead is that a law built for systems small enough and old enough that time looks the same from one moment to the next is being asked to describe the entire universe, a system that is, by definition, not staying the same from one moment to the next. The law was never wrong. It may simply never have been built to answer a question. Sean Carroll has put it plainly in his writing on the subject. On cosmological scales, energy conservation is not a law so much as a special case. It gets stranger, because if energy can effectively vanish on a cosmic scale under the right conditions, the mirror image question follows naturally. You were likely taught that energy has a flaw, that however low a system's energy might drop, there is some absolute bottom, a ground state below which it simply cannot go. But quantum physics allows for something stranger, regions where the energy density is, by measurement, less than the energy density of the vacuum itself. Less than nothing, in the sense that matters here, negative relative to what we normally define as the 0 point of empty space. In the gap between those closely spaced metal plates, the restricted vacuum can carry a lower energy density than the surrounding unrestricted vacuum outside. This has been measured. It is not speculative. Physicists have found other confirmed examples too. Certain configurations of what is called squeezed light. Laser light manipulated so its quantum uncertainty is redistributed in a particular way. These are not violations of the deeper laws of physics. The total energy averaged properly over time and space still respects the constraints quantum theory demands, but locally, briefly, in tightly bounded conditions, the numbers genuinely go negative. This matters far beyond the laboratory bench because negative energy density shows up as a required ingredient in some of the most exotic mathematical solutions to Einstein's equations of general relativity. Hypothetical shortcuts through space-time that stay open only if threaded with a source of negative energy. To be clear and responsible about this, no negative energy region anywhere near the scale or duration needed to hold a wormhole open. The confirmed examples, Casimir plates, squeezed light, involve energies almost too small to measure without extraordinarily sensitive equipment, nothing close to what exotic space-time engineering would require. This remains for now mathematics exploring what the equations permit, not a blueprint anyone can build. Still, the core fact stands, confirmed by direct laboratory measurement. The flaw most of us assume exists is not, in fact, an absolute flaw. In tightly bounded, carefully constructed quantum conditions, nature, there is a governing principle physicists lean on here, called a quantum inequality, which places strict limits on how negative an energy density can go, and for how long it can stay that way. The more negative the dip, the shorter and more fleeting it must be, as though nature enforces a kind of energy loan that always comes due. This is one reason the confirmed negative energy effects we can actually produce inside a Casimir gap, inside a pulse of squeezed light, are so vanishingly small and so brief. The math seems to permit negative energy in principle while aggressively restricting it in practice, which is exactly the kind of two-sided finding that keeps this area of physics simultaneously tantalizing. Here is the part that matters. If energy can hide inside solid matter, vanish from a cosmic ledger, and dip below its own supposed zero point, not the binding energy we already covered inside the proton, something else, something that was completely theoretical for nearly 50 years. We already walked through how most of a proton's mass comes from the confined energy of the strong force, not from the quark's own individual masses. But the quarks themselves and the electrons orbiting every atom in your body do have a small intrinsic mass of their own. The answer, proposed independently by several physicists in 1964, including Peter Higgs, was that space itself is filled with an invisible field now called the Higgs field, switched on everywhere uniformly since an instant after the beginning of the universe. Particles that interact strongly with this field are slowed, weighed down, given the property we call mass. Particles that do not interact with it, the photon, for instance, pass through unaffected, forever massless, forever traveling at the one speed the universe allows for anything. This was a mathematical proposal for nearly half a century, elegant but unconfirmed, until July 2012, when physicists at CERN's Large Hadron Collider, a 17-mile ring buried beneath the border of Switzerland and France, announced the detection of a new particle consistent with the long-predicted Higgs boson, the physical ripple in the Higgs field itself. The discovery was confirmed with a statistical significance physicists call 5 sigma, a confidence level so high that the chance of it being a random fluctuation is roughly 1 in 3.5 million. Peter Higgs, who had proposed the mechanism decades earlier, received the Nobel Prize in Physics the following year. Sit with what this actually means. Since roughly 1/10,000,000th of a second after the beginning of the universe, when the cosmos cooled just enough for this field to switch on every particle with mass in existence, inertia itself, that stubborn resistance every object has to being pushed or stopped, is, in this picture, a story about how strongly a particle drags against an invisible field, filling every point in space. This is confirmed, Nobel-recognized physics, not speculation. And yet, ask most people, what gives an object mass? What makes something heavy versus light? And the honest, complete answer, an invisible field switched on since nearly the beginning of time that we only detected directly in 2012, sounds more like a myth. The discovery itself required an almost unimaginable scale of effort to confirm. The Large Hadron Collider accelerates protons to nearly the speed of light and smashes them together roughly 40 million times per second, generating a flood of data so enormous that only a tiny fraction of collision events can even be recorded, filtered by trigger systems making split-second decisions about what might be worth keeping. Finding the Higgs boson inside that flood meant sifting through the debris of trillions of collisions looking for a very specific the same way you might infer the shape of a fired bullet only by studying the pattern of damage it leaves behind. Two independent detector teams at CERN, working with different equipment and different analysis methods, both converged on the same result in the same announcement. Here is the part that matters, and it circles back to where we started. This field carries energy. Turning it on in the earliest moments of the universe released energy and reshaped the very physics of the cosmos, is believed by many physicists to be connected to a rapid early universe expansion. Once again, energy hiding inside a mechanism most people have never heard of, quietly doing the work of holding reality. It gets stranger in the other direction now, because if energy structures everything, gives mass to matter, holds galaxies apart, seeds in the vacuum itself, there is a final, colder story waiting at the very end of it all. A story about what energy cannot do, no matter how much of it there is. Energy physicists confirm again and again is conserved. Set aside for a moment the cosmic asterisk we already discussed, and consider an isolated system. Not one joule is created, not one joule is destroyed, but there is a second law sitting beside the first one, quieter and in some ways crueler. It says that while the total amount of energy in a closed system stays the same, its usefulness does not. Every time energy converts from one form to another, chemical to mechanical, mechanical to heat, ordered motion to random jostling, some of it degrades into a less useful, more disordered form. Physicists call this quantity entropy, and the second law of thermodynamics says entropy in a closed system only ever increases, never decreases. Stars burn hydrogen into helium, releasing light and heat that scatters outward into the cold of space. Galaxies drift apart, their light stretching and weakening, faster now than ever, driven by the very dark energy we already discussed. Black holes, given enough time, an unimaginable span, but time, nonetheless, are predicted by the physicist Stephen Hawking's own calculations. Extend this far enough, and physicists arrive at a scenario they call heat death, a distant future, almost incomprehensibly far off. Not because the energy is gone, it is still there, every joule accounted for, but because it has reached maximum entropy, a uniform, cold, structureless equilibrium. No chemistry, no stars, no thought. This is not fringe doomsaying. It follows directly from the same second law of thermodynamics that governs why a hot cup of coffee cools to room temperature and never spontaneously reheats itself, a law so well confirmed across every domain of physics that some physicists consider it among the most unbreakable rules nature has ever revealed. Applied across cosmic time to the entire observable universe, it points toward the same silent, cold, changeless end. The timescales involved stretch the meaning of the word distant. The last conventional stars are expected, on current models, to burn out over roughly 100 trillion years, a span so far beyond the current 14 billion year age of the universe. After the stars are gone, some theoretical extensions of particle physics, not yet confirmed, suggest even protons themselves might eventually decay on timescales of perhaps 10 to the 34th years or longer. Sensitive searches conducted in deep underground detectors for decades. And after even that, if the black hole evaporation Hawking calculated in the 1970 seconds proceeds as predicted, the largest black holes might take on the order of 10 to the 100th years. Numbers this large stop being numbers in any intuitive sense and become something closer to a statement about how patient the universe is willing to be with its own ending. Energy itself never disappears. The one true constant, the number Feynman said we understand almost nothing about at a deeper level, will very likely outlast every star, every galaxy, every structure the universe has ever built. Perfectly conserved, perfectly still, perfectly silent. There is one more possibility that belongs here, and it needs to be said carefully, exactly as physicists themselves frame it, as a theoretical possibility. We have already established that the vacuum of space carries energy, confirmed by the Casimir effect, implicated in the cosmological constant problem, tied to dark energy itself. What we measure is the vacuum's current energy level. What physicists cannot be completely certain of is whether that current level is the lowest possible one, a true final ground state. The mathematics of quantum field theory, applied to the Higgs field in particular, has produced calculations debated, refined, and revisited over the past several decades by multiple independent research groups, suggesting that our universe's vacuum may sit in exactly, but not in principle, absolutely, permanently stable across truly cosmological timescales. If, and this remains a genuine if, resting on measurements of particle masses that still carry real uncertainty, our vacuum were ever to transition a lower, truer ground state. The physics of that transition, as physicists describe it, expanding outward at very close to the speed of light, rewriting the fundamental constants and particle behavior of everything the expanding boundary reaches. Physicists who study this are consistent and explicit on one point. This is a theoretical bound explored because the mathematics of the Higgs field or even likely within any time frame that should concern anyone living today. Some physicists favor readings of the data where our vacuum is fully, permanently stable. After all, the uncertainty in the relevant particle mass measurements, it remains honestly and by design an open, debated, low-stakes, theoretical curiosity sitting at the outer edge of what the mathematics of energy. It gets stranger only in the sense that it reveals how little confidence we can have, even in the ground we stand on, physically and figuratively, remains as unanswered as everything else in this story. Worth repeating plainly one more time, because this is exactly the kind of idea that travels badly once it leaves a physics seminar. Nothing about current observation, current measurement, or current theory suggests this is close, likely, or something anyone needs to plan around. It is a boundary condition explored in calculation, the kind of question physicists ask, not because they expect it tomorrow, but because pushing an idea the universe has already stood stable for roughly 14 billion years under whatever vacuum condition currently holds. That is the only fact anyone can respectably build a feeling out of. Return now to where this began, to a word so common it barely registers as strange energy, sitting in every equation of every branch of science. The currency. We have walked through fields that may be the true fabric beneath reality, with you as a standing pattern inside them. We have gone inside a single proton and found that the overwhelming majority of what you are made of is not matter in any old-fashioned sense. We have found that empty space is never truly empty, that it pushes on metal plates in a laboratory, that its predicted weight is wrong by more zeros. We have met dark energy, unidentified, and yet responsible for the majority of everything that exists. We have seen a sacred law develop an asterisk at the largest scales, watched energy dip below its own supposed zero, met the invisible field that gives mass its weight, and looked out toward a distant, silent equilibrium. At the center of every one of those chapters sits the same unresolved fact Feynman pointed to generations ago. We can predict it, budget it, engineer entire civilizations around converting it from one form into another. Only the number in the ledger changing form, never changing total, never once showing its face. Maybe that is simply what energy is, not an object waiting to be found, but a relationship, a symmetry, an accounting rule woven into the structure of reality so deeply that asking, what is it really, may be a bit like asking what a mile is really made of once you have already been told exactly. Or maybe there is something further down, a truer layer beneath the fields, beneath the vacuum, beneath the equations. The looking itself, the fact that our species built machines to weigh empty space and detect a field switched on at the dawn of time, is its own kind of answer, even without the final one. It always has. It is running on it right now, in the stretch of the galaxies, in the ache of your own muscles, in the quiet hum of the fields. We gave it a name a long time ago, and the name was so useful, so exact in its predictions, that we mistook the naming for understanding. We are still, all these centuries later, reading its shadow off the wall of the cave and calling it energy. Stay curious.